Section 3.2, this is going to discuss the properties of limits. Most of these will become second nature as you practice. If you have two different functions being added or subtracted, you can just add or subtract the respective limits. If you have a constant times a function, you could take the constant out, as shown in number 3. If you're multiplying two functions, you can also multiply their limits individually. Same with division. You can take out an exponent from a function and make it the exponent of the limit. These ones change a little bit. Okay, we'll talk more about compositions in a bit, and you can combine all of these to create really fancy looking limits. Example 1. Okay, we're given certain limits. We don't know what the functions are. We don't know what the constant value we're approaching is, but this is enough to help us figure out some of the bottom parts. As you can see, for example A, we could rewrite this if we want using the constant rule. I could pull this out in the front of the f of x part. I could change it, the limit as x approaches c of f of x, and then I could subtract 3 times the limit as x approaches c of g of x. Doing it that way, you can use what you have above. Okay, the limit of f of x as x approaches c is 8, so we have 2 times 8 minus 3 times -2. So we have 16 plus 6. Our answer for this would be 22. For the next one we can bring that power. Remember, we could bring that out. The constant I could bring to the front. So we have 2 times the limit of g of x as x approaches c. 2 times -2, quantity squared. So we have -4 squared, which will give us positive 16. And for the last one, it's a combination of a lot of things. All right. So again, you won't rewrite it this way. I'm just showing you the specific properties that we're using. All right, so I'm not going to write this whole thing out using all of the numbers because I noticed something. The limit of h of x as x approaches c is 0. So for this term, we'd have 4 divided by 0, which doesn't exist. It's not a real number, so the limit does not exist. And then that is our answer. This time, we're not given the specific limit values. Instead, we're given graphs, and we have to find them. So now you're using 2 different concepts as you do these problems. So we're going to have to use the graph to determine different limits. We have the graph of f, the graph of g. Okay. So here we have the limit as x approaches 0 for f of x. Well, that's going to be 2. Okay. For g of x, it's going to be 0. So we'll have 2 times the limit of f of x as x approaches 0, which is 2, and that's squared, plus 3 times the limit of g of x as x approaches 0, which is 0. 2 squared is 4. 2 times that is 8. So this is equal to 8. For the next one, we have something to do with f of x, something to do with g of x, and also another function. Okay, so as x approaches -3, we have -1, we have +1, and the limit as x approaches -3 of x squared, we know that to be 9. So putting all of those things together, we have 9 times 1 divided by -1. That's going to give us an answer of -9. So really, it's just a combination of each of these properties. Now, this is one that could cause some people trouble because it is a composition, and we can't just write it. We can't just pull it out like this. It doesn't quite work that way. It's close, but not quite. All right, let me erase that. So what we have to do instead, we take the limiting value, x approaches -3 of f of x. Start with the inside. So you get -1. So really now we're going to do the limit as x approaches -1 of g of x. Okay, and now if you look as x approaches -1 of for g of x, the limit, although the function value isn't there, the limit value is 1. All right, let's try one more of those. So the limit as x approaches -1 of x squared will be 1. So now what is the limit as x approaches 1 of g of x, that function? Well, for that we just need the graph. As x approaches 1, it appears that the graph approaches -1. For section E, I would like you to do that in your WISC when you fill out that for this specific video. I want you to do this problem and write your answer in the WISC. And then we have this one over here, okay? So we have 5 minus, and there's a lot here. If you need something explained, just ask in class. -1 for x squared, that's simply going to be 1, okay, times 3 plus. Now if we take a look at f of x, as x approaches -1, we have this and this. So that limit does not exist. So this whole thing is a non-existent limit. So at this point, you could do probably any of the portions of 1 or 2 on your worksheet. So that'd be a good thing to work on tonight. And then I just want to cover the basics of our next topic. So with a calculator, you could do this on your own. If you try to do this on your limit, and again, you could type in the function into y1, look at your table as the x values get closer and closer to 0, and see what it's approaching. All right, in this case, it turns out it's approaching 1, and it turns out this one's approaching 0. These will be a big deal as we move forward in this section. So in general, for these cases, as long as g of 0 is not 0, these limits will always be these respective numbers. So if we have the limit as x approaches 0 of sine of 5x over 5x, notice how these are the same thing, then that limit is going to equal 1. Okay, we have 1 minus cosine of x over 2 over x over 2, they're the same function. So the limit as x approaches 0 of anything in that form is going to be 0. Here, this one's a little bit different. Although we do have g of x and g of x, see, just like that, the limit isn't approaching 0. Instead, it's approaching 7. But that's not going to trick us because we know properties of transformations of functions. If you do x minus 7, really, you're just moving the function 7 units to the right. So if we move the function 7 units to the right, and you move our limit 7 units to the right, then this is going to be this form, and we can just say it would be 1. All right, so this is our last example we're going to cover. I'm not going to do all of these. I just want to start to show you some limits that now you're going to be able to do. We don't have something in this form, but we are smart. We know algebra, so we could rewrite it as x over x plus sine x over x. X over x, of course, is just 1. And sine of x over x, we know the limit of that as x approaches 0 is simply 1. So we have 1 plus 1. This limit equals 2. For the next one, we don't have anything to do with tangent of x, but we can do a little bit of manipulation here. So I have the limit as x approaches 0. Instead of writing tangent, one thing I could do is write sine over cosine. We shouldn't have a complex fraction though, so if I multiply the top and the bottom by cosine, this time I'll get the limit as x approaches 0. I have x over sine of x times cosine of x. Now I can do this limit because I know the limit as x approaches 0 of x over sine of x which is in a very similar form of this one. Okay, they're going to have the same limit value. That's going to be 1. But now what's the cosine of 0? And you should know that as 1. So the limit, this limit equals 1. All right. This third one, a little bit more of manipulation and it'll look great. It looks kind of close to the cosine limit that we have above, but not quite. So we can change it. And if you are smart, you probably already know what to do. If you divide every single term by secant of theta, watch what happens. Okay, the limit as theta approaches 0. Secant over secant is 1. 1 over secant is cosine. Theta times secant divided by secant is just going to be theta. This looks exactly like this up here, so we can assume that the limit is 0. All right, so these 3 problems we will finish in class. If you want to try them, it won't hurt. Okay, there's some neat things that you could do with algebra, which save you from having to memorizing a whole bunch of things later on. All right, so don't forget to fill out your WISC, and I'll see you in class.